Hello, I'm Dr. An. In this video, I'll be talking about many different types of forces that you'll be encountering in physics problems. And most importantly, I'll be introducing something called free body diagram that will be crucial in solving physics problems. In mechanics, we have tension force, normal force, applied force, such as pulling and pushing. Friction force, we're going to be talking about static and kinetic friction forces. Spring force, drag force, such as in air or in liquid, a buoyant force, specifically in liquid, and the gravitational force. In electricity and magnetism, there are electric force and magnetic force, which we can combine and call them electromagnetic force. And in nuclear physics, we have weak nuclear force and strong nuclear force. For these forces on the left column to be produced, objects need to be in physical contact with each other. On the other hand, for these forces on the right column, objects are experiencing the forces even when they're not in contact with each other. So in mechanics, we'll deal with all these forces on the left and the gravitational force on the right. Well, let's begin with guidelines for drawing a free body diagram. When you draw a simple diagram representing the problem, use either rectangles or circles to represent the objects. And draw a dot in the middle of each object of interest. And this dot means that even if we draw the object with a sizable box or a circle, we're treating it as a point particle that has no dimensions. Draw all the forces that are exerting on the object, using the arrows representing vectors. And tails of all the arrows must originate from the center of mass of the object, which is represented as a dot. Well, let's get acquainted with free body diagram guidelines with this first problem, which deals with tension force and the gravitational force. When you are whirling a stone with a string attached, and when it's circling with a constant speed, we call this motion uniform circular motion. In this specific problem, this circular motion is in the horizontal plane. Well, first thing is draw the object with either a circle or a rectangle, right? Here it's already drawn with a circle. All right, it's good. Next, we need to represent this object with a dot. Finally, draw all the forces acting on this object with tails of force vector originating from the dot. In this case, we have tension force from the string and gravitational force from the earth. That's all. And let's take a look at this snapshot of motion along the horizontal plane. And this is the completed free body diagram for this case. Let's take a look at a couple more cases where objects are suspended in air with strings attached. If a pendulum is swinging, there is a tension force from the string, and of course gravitational force from the earth. And if an object is suspended by two ropes like this, there are two different tension forces on each rope, along with the gravitational force. Well, let's go to our main menu. Next, we'll have examples where these four forces, normal force, gravitational force, applied force, and friction force, are exerted on the object. First, let me explain what normal force is. In math and physics, the word normal means perpendicular. And the definition is the following. The normal force is the support force that is perpendicular to the surface that the object is in contact with. So when the object is on the level floor, this is the normal force acting on the object by the floor, which is perpendicular to the surface it is in contact with. If an object is on the inclined surface like this is the normal force acting on the object by the floor. Again, which is perpendicular to the surface it is in contact with. If an object is pushed against a vertical wall, even with an angle, the normal force is again perpendicular to the surface that it is in contact with. Oh, by the way, these arrows just represented normal forces, which are just part of the free body diagram. Okay, so let's do complete free body diagrams. Case number 1, the object is on the level surface. Let's say it's on the level table. Okay, when there is no friction between the object and the table surface, there is a gravitational force on this object by the earth, and to resist that force, there must be a counteracting force so that the object doesn't sink into the table, right? Which is normal force on the object by the table. And if there is no additional force acting on it, this is the completed free body diagram. However, if there is an applied force, for example, let's say you attach a rope and pulling the object at an angle like this, then the normal force will be a little less, and this will be a completed free body diagram. We'll be talking about the details in the later video. Here I just want to focus on what kind of forces you need to draw in what direction. Okay? Next, let's say we have an object on a rough level floor, and the object is not moving. Okay? Then as usual, we have gravitational force, and let's say we're pulling the object this way. Then we have the corresponding normal force that is perpendicular to the floor. And since the object is not moving, the friction force must counteract the applied force. So it's this way, opposite to the direction at which the object would have moved if there weren't this resisting force. Oh, by the way, friction force is always opposite to the direction in which the object is moving or trying to move. And this completes our free body diagram for this case. Now, let's consider a case where the object is on the rough level floor, but it is moving. Well, just like our previous case, we would have gravitational force and applied force that pulls the object and the corresponding normal force. But as we said, let's say the object is moving to the right. Then instead of static friction force, we have something called kinetic friction force because it's moving. And this completes our free body diagram. I'll teach you on the details of these two friction forces in the later video, so don't worry about it. In this video, just remember to use static friction force when the object is not moving and use kinetic friction force when the object is moving. Now, case number 2. The object is on the inclined surface. And let's say the surface is frictionless. In other words, no friction force on the object. Then as usual, gravitational force and the normal force that is perpendicular to the surface it is in contact with. And that's it. Now let's suppose the object is on the rough inclined surface and the object is not moving. Then as before, we have gravitational force and a normal force. Now, if we let go on the frictionless surface, the object will slide the inclined surface, right? So to resist this motion, there is this static friction force. And this completes our free body diagram for this case. Now, let's say the object is again on the rough inclined surface, but the object is moving down the surface. On top of our usual gravitational force and normal force, let's say we're constantly pushing the object or pulling the object with applied force like this. And suppose it is moving down the inclined surface. Then since the friction force is always in the direction opposite to the movement of the object, we have this kinetic friction force. Kinetic because the object is moving. And this completes our free body diagram for this case. And let's move on to case number 3. Let's think about a case where the object is pushed against the vertical wall. First, on the frictionless wall, so no friction force involved, there's always this gravitational force. And let's suppose we're pushing the object like this, then there will be corresponding normal force like this, which is perpendicular to the surface that it is in contact with. And this is it for this simple case. Now let's say the object is pushed against the vertical wall with a rough surface, and the object is not moving. So we have a situation for static friction force. As usual, we have a gravitational force, and let's say we're pushing this object like this. Then there will be corresponding normal force like this, and since it's not moving, there is a static friction force upward to resist this sliding down motion. And this is the free body diagram for this case. Now let's suppose we're pushing the object against another rough vertical wall and the object is sliding down. Then we have this gravitational force and we're pushing this object like this and we'll have the normal force. Well, since it is moving down, we have the kinetic friction force opposite to its movement, like this. And this is the completed free body diagram. All right, back to our main menu. Now we'll consider cases with springs. Case number 1. We have an object attached to a spring like this, and this dotted green line indicates the position of the object where the spring is neither stretched nor compressed. In other words, the spring is relaxed when the object is in that position. And we're going to pull the object to stretch the spring. Then the spring will exert a force in the opposite direction to get back to the relaxed position. And this is the completed free body diagram. Now, case number 2. Originally, the spring is in the relaxed state, and now we're going to push the object to compress the spring. Then the spring will exert a force on the object in the opposite direction to get back to the relaxed position again. And this is the free body diagram. And moving on to case number 3, we'll pull the object to stretch the spring and let go this time. We're going to release the object after stretching the spring. So when we pull the object like this and stretch the spring, there will be a spring force in the opposite direction, right? Now, if we let go, we don't have this applied force anymore. And this is the final free body diagram for this situation. So without any applied force, this spring force makes the object oscillate back and forth like this. Now, during this oscillation, when it is compressed like this, what do you think our free body diagram will look like? Well, as usual, gravitational force and normal force, and the spring force will be exerting on the object to push to the right to get back to the relaxed position. And this is the completed free body diagram when compressed. And anywhere in between the endpoints of oscillation will have different amount of spring force depending on how much is compressed and stretched. We'll learn all this in the following video. Back to our main menu, and we have our last example. We'll look at a couple of cases where drag force and buoyant force are present. Just a taste of it. I'll have separate lesson videos for these topics. So here is a brief introduction, okay? Whenever an object moves through a medium that has certain density, such as air and water, there's a drag force that is opposite to the motion of the object. Here is a parachutist or parachuter who jumps off the airplane, and during his free fall, air creates a drag force opposite to his movement. And of course, there is a gravitational force on him. When a fish swims in water, again, the drag force is exerting on it to the opposite direction of its movement. And other forces include gravitational force and something called buoyant force that is present in any liquid media, and some applied force such as the water current and by its own muscle power to swim forward. Okay, you should feel very comfortable creating free body diagram in different physics problem situations now. Now let's use this technique to solve some physics problems. I'll see you in the next video.